Good afternoon. This is our lecture 032, Surface Water Hydrology. The course number CIVE 634. It's a graduate class at San Diego State University, Department of Civil Engineering. Today we're going to be talking about the calculation of evaporation and evapotranspiration. And I'm going to specifically talk about four formulas. Okay, we are going to be covering four formulas. Two temperature formulas, Blaney-Criddle and Thornthwaite. And then we're going to move into Penman-Monteith. We already covered Penman last week. And we finalized today's class with Shuttleworth. Hopefully we're going to be covering from B03 to B11. I don't know if we'll have the time, but we'll try to play it by ear and see where we get. So the first thing I need to do is go back to over here and get into the first temperature model. Okay, so as I said, we are going to be first looking at the temperature models to estimate evapotranspiration. Over there. And there are two classical temperature models. The first one is called the Blaney-Criddle formula, and the second one is the Thornthwaite formula. These formulas, the references tell us that they're at least 50 years old. I can remember when I was an undergrad, I studied the Blaney-Criddle formula back when I was in Peru, when I was studying in Peru, my undergrad. Civil engineering undergrad. So the Blaney-Criddle is an old formula. It was very much in use 50 years ago, as well as the Thornthwaite formula. Now, the story is that while the Blaney-Criddle has a tendency to be more or less accurate, the Thornthwaite formula is not. However, it is a very simple formula, the second one, the Thornthwaite formula, and one that is very much used out there by people that they just want to get a number, even though it may not be quite accurate. And the reason is because the Thornthwaite formula only requires temperature. So, and temperature is relatively easy, as a piece of data is relatively easy to get. So let's first take a look at the Thornthwaite rather than the Blaney-Criddle formula. The Blaney-Criddle formula is typical of the temperature models for the estimation of evapotranspiration. It was at one time recommended by FAO of the United Nations, the Food and Agriculture Organization. I believe it has now been superseded. However, for the sake of history, we cover the Blaney-Criddle, although I'm not going to spend a whole lot of time on it. Besides, we already must know or must realize that we have calculators for all these methods, beginning with the simplest ones, such as the Blaney-Criddle, following with Thornthwaite, then we get to Penman-Monteith, and finally we even have a calculator for the very complex, and you'll see it later today, the Shuttleworth-Wallace formula. It's my estimation or my understanding is it's ridiculously complex, and you'll see it I would say in about an hour. So let's take a look at Blaney-Criddle. The origination of Blaney-Criddle was done for a monthly and in terms of English units, or rather American customary units, US customary units. That is the proper name, feet pound. So F would be evapotranspiration for a given month, P a day length variable, defined as the ratio of the total daytime hours for a given month to the total daytime hours in the year. So it had to do with the insolation per month. You know, depending on the latitude, there's variation in the amount of insolation, which is the exposure to the sun. T is the temperature in degrees Fahrenheit. Subsequently, this formula was used throughout the world, and people saw fit to convert it to the the SI units. That is commonly referred to as the metric system. And they preferred to apply it on a daily basis. So the Blaney-Criddle formula, the more common formula that is written in the books, appears as 240 here, as equation 240. It's the same equation. It's just that it has been converted into units and expressed per day. F is now, lowercase f is the daily consumptive use factor in millimeters. P is the ratio of mean daily daytime hours for a given month to the total daytime hours in a year, is a percent. Now we're looking at it as a percent, a function of latitude. Table A3, we can go to table A3 in the appendix. I've actually I have made this clickable. And T is the temperature, mean daily temperature for a given month in degrees Celsius. In addition to this, the consumptive water requirement is the amount of water required to meet its evapotranspiration needs without being limited by lack of water. And the consumptive water requirement under this formula is equal to the consumptive use factor, F, calculated by 240, times an empirical consumptive use coefficient, K sub C. And we will show you tables to determine the K sub C. Okay, over the years though, the Blaney-Criddle formula, the original Blaney-Criddle formula, has been modified, changed. There's the formula by Dorenbos and Pruitt, who has received wide endorsement throughout the world in its time, maybe 30, 40 years ago. And they proposed a correction. And the correction was expressed by a graph. This is the graph of Dorenbos and Pruitt. Don't forget that at the time when this work was done, maybe 40 years ago, graphs were very popular. It was the way to do it. People studied graphs. I can remember when I was going to school as an undergrad, I took 2 classes in graphing. Can you believe that? They don't have that anymore. It's gone by the wayside. Most of the stuff is now done digitally, more so on the web. I was going to mention that all these methods are really nice, but in practice, what you're going to do most likely is use one of the many calculators that are out there, including mine. I have a calculator for every one of these formulas. The web has produced an increase in the productivity. In the past, it will take you 3 hours to do this calculation. Now, if you go to one of the calculators, it'll probably take you 5 minutes. You put in the data and that's it. And that's the way it's going to continue because it means increased productivity. So you're going to have to trust those people that develop the calculators. If there's any question of errors, of course, you can always bring it up. If you prove that, in fact, one of my calculators is wrong, and I've already mentioned this to you, I would fix it. And in the last 15 years since I've been doing calculators, I've had to do this operation of correcting one of my calculators twice in 15 years. Okay, so these are the graphs by Dorenbos and Pruitt. I believe these gentlemen are Dutch. Their names sounds a little bit in that category. Furthermore, we have other people like Frebert. Frebert was a great contributor in this field that developed regression equations so that we wouldn't have to go into the graphs. With the regression equations, you just put that regression equation into the calculator or into the Excel sheet. And these are somewhat complex regression equations, but they are there for us to use. And finally, the table 2.7 shows the crop coefficients, seasonal crop coefficients. Alfalfa, avocado, bananas, and look, there's a range for it, which means that we can't really tell exactly what the evapotranspiration is going to be. There's going to be a variability in there. Remember I mentioned to you that in hydrology there's a 20-30% variability, which is acceptable. In this case, for instance, for the case of onions, we're looking at 25 to 40. 25, that's more than 30% right there. And that's a variability that is well accepted in practice. I should mention to you as we start this subject though, that over here it says that you got to multiply that the calculation that we have in here is ETO, which is the reference crop evaporation. Reference crop. What's the reference crop? The reference crop is it's a grass of a certain size and of a certain quality. But if we want to apply this formula to other crops, then we would have to multiply the reference crop evapotranspiration times the crop coefficient, which are given in the tables. And that's the number that should be applied to the crop. Is that true? Isn't there anything else out there? And the answer is yes. If you apply the evapotranspiration multiplying the reference crop by the K sub C, you're going to get a number. That's the number that the plant will use. But in reality, when you're out there in the field, you've got to add a little more water because it's an irrigation problem. You're going to have to remove the salts that are coming in with the water. Every amount of water, no matter where you get it, has a certain amount of salt. And the evapotranspiration process is going to take care of the water. It's going to evaporate the water, but it's going to leave the salt behind. So you're going to have to provide extra water, not for the plant's benefit, but rather to drain the water by gravity. The drainage has to be by gravity. There's got to be a gradient for moving the water out. And that's what we call drainage. And in the real world, irrigation is always together or coupled with drainage. We got to drain the soil. If we don't drain the soil, eventually the people are doing the irrigation are going to go out of business. The numbers for the drainage, it's called the leaching coefficient, could be maybe 10, 15, 20%. That has to be calculated. In our environmental hydrology class that I taught last year, we teach you how to calculate the leaching fraction for the salinity. So that's kind of another problem. It's not related to the problem we're talking about here. So we have an example here. Calculate the reference crop evapotranspiration by the Blaney-Criddle method during the month of March, location at 35 degrees north, daily temperature 18 Celsius. Assume medium insolation, medium minimum relative humidity, and moderate daytime wind speed. Those are the parameters of Dorembos and Pruitt. So let me remember here what I'm going to do. I'm going to run these calculators so that you can see how easy this thing gets, okay? And you already seen it before, but let me just reiterate on this. So it's the month of March, location 35 north, 18 degrees Celsius. So let me go over here, and we're going to say, what month is it? March, latitude 35, mean daily temperature, I think I said 18, right? Hemisphere is north. And in here, actual insolation is going to be medium, medium, and daytime wind speed, moderate. And the type of crop is going to be the reference crop. So the calculation is the monthly ETC, daily ETC, monthly ETC is 122.9 millimeters. In this case, because the reference crop has a K sub C coefficient equal to 1, the ETO, which is the reference evapotranspiration, is equal to the crop evapotranspiration. Okay, so we go back in here, and sure enough, in here we have 122.9 millimeters. So I have confirmed, for you, I have confirmed that this calculation in my book was done correctly. Let's proceed now to the Thornthwaite method. The Thornthwaite method is another widely used temperature model to estimate potential evapotranspiration. The method is based on an annual temperature efficiency index, J, defined as the sum of 12 monthly values of heat index I. Each heat index is a function of the mean monthly temperature T in degrees Celsius. So the index is, you would take the mean monthly temperatures, we find these heat indices, and we calculate evapotranspiration by the following formula. And J is the sum. J is the sum of the 12. So we calculate first the monthly heat index, then we sum all of them, we calculate the J, and then we put the T over here for every month, or in the J, which is the sum of the annual temperature efficiency index. So this formula looks kind of complicated, but algebraically is very easy to do. And in our calculator, as you can see, it's going to work really well. Now the C coefficient, though, it's a correlation. It's actually, I guess you could call this a spline. I don't know if you're familiar with that word. So a spline is a fit. It's a nonlinear fit because usually the correlations are linear fits, the typical correlations. But if you use software, you can calculate splines. A spline is typically an equation like this, 245, where you have a power function, a very complex power function. So that's for the exponent. That's the C of the PET, where PET stands for potential evapotranspiration. And we have a table to this formula of 245 applies at 0 degrees latitude. But if we are at some other latitude, we would have to make a correction for the other latitude, where K other than 0, the latitude other than 0, where K is a constant for each month of the year, varying as a function of latitude. See table A4. We can go to table A4 of the appendix. I have already shown to you where the appendix is. If you want to go to the appendix, you go to my book, to this book. And on the top of my website or the page, the syllabus page for this class, I have a link to my hydrology book. Okay, so in here, we're going to do this. We're going to take these data, the temperature data, 2, 4, 6, 8, 10, 12, correct. So I'm going to copy over here, and I'm going to do the calculation by the Thornthwaite formula during the month of July for 30 degrees north. Okay, that's what I'm going to do. Use Thornthwaite during the month of July over here for 30 degrees north, and the temperature is that, and we get the monthly potential evapotranspiration is 12.227. 12.227 over here. So if we go to the example 2.7, the answer is 12.227. So I have proven to you that we did the problem correctly. The problem was solved right now correctly to use the Thornthwaite method. As you can see, these calculators allow us to do a whole lot of calculations. What they cannot do, though, is do a loop. If you want to do a loop, then I guess you're on your own, or you can do an Excel sheet, or you can get into programming yourself. And you can do all kinds of loops when you have programming, when you have your knowledge of programming. Changes are happening now. People are getting more adept at programming because we have realized over the years that we have to get back into programming. I know some of you will say, I already program with Excel, which is fine. I have no argument with that. I'm not going to quarrel with anybody that says that. Radiation models, I'm going to skip because it's a model that is not that important and is not very much used in my experience. So I'm going to skip the radiation model. And at this point, what I'm going to do is I'm going to go back to the syllabus right here. So we're done with this, okay? And now I already covered that. I already ran for you an example on the Penman method, so I'm not going to do that. So what I'm going to do now is directly go into the meat of today's class, which is the Penman-Monteith method. And what I'm going to do, since this is very important, what I'm going to do is I'm going to do the raster first to get you going on it. But since the raster is fast and does not allow for us to regulate the speed of presentation, I'm going to first do the raster, and then don't get too worried if it's too fast. We'll do the vector too. In other words, we'll do first do the video and then the vector. There's going to be a lot of new terms in here. For those of you that are not in this field or not particularly good with your chemical formulas and so forth, bear with me. All of us have had to do it. The Penman-Monteith method is an interesting method because it is explained in only a few references. And to be honest with you, most of them, if not all, are all messed up. They have errors. I have had to work extremely hard to get this thing to make sense, at least to me, and I'm hoping that it will make sense to you. So bear with me. We have to go through this. For some people, it may be a pain, but so be it.
The Penman-Monteith combination method for the calculation of evaporation is reviewed and clarified. Unlike the original Penman model, in the Penman,
I will say in there reviewed and clarified, because if you go like to the manuals that are around, oh, you spend months out there trying to figure out what they did. We clarified it.
Model, the mass transfer evaporation rate is calculated based on physical principles. An illustrative example is worked out to clarify the computational procedure. An online calculation using online Penman-Monteith gives the same answer.
In order to talk about the Penman-Monteith formula, we first have to introduce the Penman model.
The original Pinman model is a combination method in which the total evaporation rate is calculated by weighing the evaporation rate due to net radiation and the evaporation rate due to mass transfer, as follows.
Okay, here it is, the evaporation rate due to net radiation, and here's the mass transfer. And the weighting factors have delta and gamma, which are properly defined. That is the combination method of Penman. That's how he got famous. Never mind that this stuff in here is a conceptual model, meaning it works well, everybody uses it, but we have not been able to document 100% its deterministic components. But it's a good method. It's the best, as a matter of fact. Actually, I take that back. The Shuttleworth-Wallace is supposed to be better, but it's so complicated that I do not believe too many people are using it.
The mass transfer evaporation rate E sub A is calculated with an empirical mass transfer formula. In the Penman-Monteith model, the mass transfer evaporation rate E sub A is calculated based on physical principles. The original form of the Penman-Monteith equation in dimensionally consistent units is the following.
Notice that in here, instead of having a Dalton type, we in fact have a Dalton type, but Dalton did not put in there rho sub A, C sub P, and R sub A. That's the difference. Plus, the other difference is that while Penman had a gamma, Penman-Monteith has a gamma star. It's a modified way of looking at gamma. By the way, our equations, the ones that I presented here, are dimensionally consistent, meaning every one of these responds to some units that make sense. All in all, everything would have to be dimensionally consistent. Otherwise, you'll be adding up or multiplying apples and oranges, and that should not be the case.
The quantity R sub A to the minus 1 is the external conductance in cubic centimeters of air per square centimeter of surface per second. In evaporation rate units, equation 2 is expressed as follows. Equation 4 is the Penman-Monteith model of evaporation. The density of dry air at 0 degrees Celsius and sea level atmospheric pressure is rho sub AD equal 1.2929 kilograms per cubic meter. The density of moist air, rho sub A, may be approximated as follows. For instance, at T equal 20 degrees Celsius and sea level, that is standard atmospheric pressure, rho sub A is equal to 0.00120046 grams per cubic centimeter. The specific heat of moist air in the temperature range from 0 to 40 degrees Celsius is C sub P equal 1.005 joules per gram per degree Celsius. Converting to calories, C sub P equal 0.2402 calories per gram per degree Celsius. In evaporation units of centimeters per day, equation 4 is expressed as follows.
We are bringing in the constant 86,400 because it is the number of seconds per day, and we want to put it per day.
Equation 6 may be conveniently expressed in Penman form as follows. Comparing equations 6 and 7, the evaporation rate due to mass transfer is obtained.
Basically, what Dalton did 220 years ago is this. He said that evaporation is this number here, E sub S minus E sub A, multiplied by a so-called wind function. So Dalton said this whole thing over here was the wind function. Now, the so-called wind function. Now we're putting in there specific chemical values, chemical variables and values. The contribution of Monteith.
Simplifying equation 8, in which K is equal a constant varying with air temperature and atmospheric pressure in units of seconds per day millibar, expressed as follows. In equation 10, the units of rho sub A, C sub P, rho, lambda, and gamma are the same as in equations 2 and 4. The psychrometric constant, gamma, in millibars per degree Celsius is.
The psychrometric constant is called a constant because of practice, but it's really not a constant. It varies within a very narrow range.
Substituting equation 11 in equation 10. in which the constant K remains in units of second per day per millibar. Replacing R sub MW equal to 0.622 in equation 12, in which the constant K remains in units of second per day per millibar. At temperature equal 20 degrees Celsius and standard atmospheric pressure, sea level, rho sub A equal 0.00120046 gram per cubic centimeter, rho equals 0.99821 grams per cubic centimeter, and P equal 1013.25 millibars. Thus, the constant K in equation 13 reduces to K equals 0.064 seconds per day per millibar, and equation 9 reduces to
The Penman-Monteith method differs from the Penman method in that he identified the resistances, the two resistances, R sub A, which is the external, also referred to as aerodynamic resistance, and the units are seconds per centimeter, and R sub S is the internal or stomatal or surface resistance, is also in seconds per centimeter. So Monteith is going to estimate, determine, or if he can't determine, he'll have to estimate values of R sub A and R sub S, without which he obviously cannot proceed with the method. By the way, the people that have given up on the Penman-Monteith as a method do so because they have difficulty finding the values of R sub S and R sub A.
the external or aerodynamic resistance, R sub A, varies with the surface roughness, water, soil, or vegetation, being inversely proportional to wind speed. In other words, the external conductance and thus the evaporation rate increases with wind speed as originally proposed by Dalton. The external resistance for evaporation from open water can be estimated as follows. The external resistance R sub A in seconds per meter for the reference crop, that is, clipped grass, 0.12 meter high, for measurements of wind speed in meters per second, temperature and humidity at a standardized height of 2 meters is. For instance, for V sub 2 equal 200 kilometers per day equal 2.31 meters per second, the external or aerodynamic resistance of the reference crop is. The internal or stomatal or surface resistance, R sub S, is inversely proportional to the leaf area index, L. An empirical relation for surface resistance is the following. The leaf area index, L, is empirically related to crop height, H sub C. The leaf area index for clipped grass is. From equations 18 and 19, the surface resistance of the reference crop, that is clipped grass 0.12 meter high, is R sub S RC equal to 200 divided by 24 times 0.12 equals 69.4 seconds per meter. The leaf area index for alfalfa is the following. From equation 20, for H sub C equal 0.3 meters, the leaf area index for alfalfa is L equal 3.69. From equation 18, the surface resistance for alfalfa is R sub S equal to 200 divided by 3.69 equal 54.2 seconds per meter. Calculate the evaporation rate of the reference crop by the Penman-Monteith Method for the month of April for the following atmospheric conditions. Air temperature T sub A equal 20 degrees Celsius. Net radiation Q sub N equal 550 calories per square centimeter per day. Wind speed V sub 2 equal 200 kilometers per day. And relative humidity phi equals 70%. Assume standard atmospheric pressure. The saturation vapor pressure gradient is the net radiation in evaporation rate units is using equation 16, the external resistance of the reference crop is the internal resistance of the reference crop is from equation 11, the psychrometric constant is from equation 3, the modified psychrometric constant is the vapor pressure deficit is
Note in here the small change. We go off vapor pressure deficit is E sub S minus E sub A. But we're replacing here the E sub S for E sub O. E sub O is the with temperature of the water, and here is the temperature of the air. Or rather, no, that's not correct. But the point is that we can replace the E sub O for E sub S. And we get we take E sub O out, and this is what we get in here. I'm going to get the red out of here, but it doesn't want me to do it. Okay.
From equation 14, the mass transfer evaporation rate is from equation 7, the total evaporation rate is E equal 0.644 centimeters per day. The evaporation rate for the month of April is E equal 30 times 0.644 equal 19.32 centimeters. Using online Penman-Monteith, the answer is daily reference crop, PET, equal 0.644 centimeters per day. Monthly reference crop, PET for April, equal 19.32 centimeters. These results are the same as the hand calculation shown before.
Okay, so we have seen the video of the paper. So now we're going to take a quick look at the paper. because obviously the video goes at a certain pace, and sometimes perhaps you want to spend a little more time looking at this and making sure that you understood everything that was said. So this is the paper that originated the video. So everything that's in the video, it's in the paper. But now you can look at this at your own pace. The original formula for the Penman model, it's number 1. The Penman-Monteith method puts in here, instead of gamma E sub A, we now have an expression which is physically more consistent, I guess you could say, more meaningful. Note that we have changed from E, which is total evaporation rate, to over here is the energy flux. And we do that by multiplying E times rho lambda. And I already covered, when we looked at the book, the rationale for this equation to convert energy to evaporation rate units. So we need to keep that in mind, because once we fix the left, the right is also going to fix. This is energy, while this is evaporation rate units. But everything that we say in here is consistent. By the way, I did mention, or I neglected to mention, that this treatment is part of the Maitman Handbook of Hydrology book, 1993, which I consulted in order to write this paper. And I should say that whoever wrote the chapter, because the Maitman, it's a compendium. It's a very thick book, and every chapter has a different author. And I do not recall who the author of this chapter was, but whoever wrote the chapter did a great job. But there were a few bugs that, unfortunately, Professor Ponce had to go through and clarify the bugs, going to other reference and so forth. I've done this, maybe 20 years ago, so I don't remember the details. But the point is that we did clarify the math. The algebra is correct. We had to do that. We could not attempt to do the calculation, or rather to build an online calculator without knowing how exactly it was that the method was proceeding. Okay, so we have all the definitions in here, and this is repetition, but so be it. The gamma star, it's now the gamma multiplied times 1 plus R sub S over R sub A. And remember, these two constants are the ones that distinguish the Penman-Monteith method from the Penman method. And finally, we get over here, and you're at liberty to spend as much time as you wish with these, though. However, I am going to ask that you run the calculators, because that's what you're going to be doing in the future. Now, if at any time in your work you need to get back to these equations, you know where to get them. You know where to get them. They're always going to be there. Or else, at a pinch, you can go back to the manual by Professor, I can't remember the name right now, Maitman, Professor Maitman from University of Texas, who wrote the manual in 1993. The physical constants, the daily evaporation rate, and when we get into the daily evaporation rate, we got to bring in the 86,400 product in there, because that indicates the number of seconds in a day. Number of seconds in a day. And we finally get to the equation, the Penman-Monteith equation in Penman form. That is equation 7. The only difference is that instead of having a lambda, we have a lambda star. And now we calculate the E sub A, which is more of the details as to how to make sure that the Dalton term, the E sub A, is calculated correctly. So we have, I myself introduced the K in there just to simplify the algebra, because otherwise the equations were getting very long. So I figured, I said, well, let me try to simplify things here. So the K is really my own creation. The replacement to make the equations more readable, I guess you could say more legible. The psychrometric constant, gamma, and we'll prove later on that there are is not really a constant. It's referred to as a constant because at the beginning, the people that developed these theories thought it was a constant, but it really isn't. It has a very, very small range of variation. I believe from 0.66 to 0.69, something like that. And we finally get to the E sub A, as we did in the video. We cover the external resistance, and then we cover the internal resistance, as we already done in the video, and then we go to an example, and the example is there for you that you can follow it. I believe in here, the references are even can be clicked, so you can go directly to my book to show how we did this. Section 2.2 of my book, 2014, my electronic book, because the first edition of my book was published in 1989, and the second edition, which was entirely online, is 2014. The difference, of course, is the 1989 book, you have to pay for it. I believe it cost maybe $100 in Amazon, while the 2014, which came slightly better because there were some corrections or omissions. There were maybe the online book is maybe 10% better because it has corrections and fixes that we at the time we did this originally in the date 1989, we were not aware that these things could happen. So the point is that I believe that the 2014 book is a better book, cheaper, of course, it doesn't cost anything, and it is totally online. Plus, it is alive, meaning I can change it at any time. And as a matter of fact, the other day, I think we came to the realization that there were a couple of references, they had the wrong number. So I'm going to do that in the next couple of days to correct those references. As you can see, the online book has the advantage that it can be corrected on the go. You can't do that with a book that was printed. So we finally get to the solution, to the answer, and the Penman calculation, which I already have done. And I have a picture of here of one of my servers. I have actually 3 servers to document my work because I need backup. I cannot afford to have only one server. One server, if the server dies, then I'm dead on the water. No, I have 3 servers, and we back them almost every day from one server to the other 2, which are my backup servers. And that's the way a server looks, by the way. A lot of people are saying these days that servers are no longer needed. I disagree with that. I believe that it is better that to own the house than to rent it. When you don't own a server, you're renting space somewhere. They could do this and that, not even ask you permission. But if you own the place, you own the house, then they have to ask you permission first. Okay, so I do believe, and I've worked with servers for, I don't know, 30 to 40 years. Even before the web, we were already using servers, by the way. 1989 is when I bought my first server. Can you believe that? That's 33 years ago. Okay, so that's the end of this. That's the end of this. And now we go to the psychrometric constant. And in here we have a video and a vector. I'm just going to go with the vector here today. We're going to go with a vector just for variety, although everything I say here in the vector is also in the video. So the first thing is the Bowen ratio. Bowen was a very important gentleman. He developed this ratio. I guess the ratio is attributed to him because he was a very well-known, great contributor to the science of meteorology. So Q sub H and Q sub E. What's Q sub H? Q sub H is the sensible heat transfer from water body to the atmosphere. And Q sub E is the energy expended in the evaporation process. So the Bowen ratio varies with the weather, with the climate. It's different, it's opposite or rather different from an arid climate to a wetter climate such as, for instance, the Amazon. Compare the Sahara with the Amazon. They would have quite different Bowen ratios. And the Bowen ratio is a direct indication of the weather. T sub S, water surface temperature, T sub A, overlying air temperature, E sub S, saturation vapor pressure at the water surface temperature, and E sub A, the water vapor of the overlying air. a minute ago I talked about this and I said because we could not get this the E sub S, we replaced it for E sub O, and that is correct because that's a saturation vapor pressure at the water surface temperature, but the water surface temperature is hard to get. So we normally get the air temperature, and the air temperature is not E sub S, but E sub O. And that turns out to be easier for us in order to do our calculations. So usually the E sub S is always replaced for E sub O in these calculations. The psychrometric constant, according to all books like Meitman's, is this definition, equation number 2. And when we plug in the numbers, we get a gamma as a function of lambda, which reduces to gamma psychrometric constant is equal to 391.24 divided by lambda, where lambda is in calories per gram. So for any atmospheric pressure, we got to put the P in there, and therefore we have the gamma in there, which reduces to equation 6. With P in millibars, that's the atmospheric pressure. Gamma in calories per gram, that's the gamma is the latent heat of water vaporization. So with that, then we can calculate the gamma. Calculation of the psychrometric constant, we call it constant just because of usage, but it's not a constant. Otherwise, we wouldn't be able to put it in a table, right, if it were a constant. But you can see that the number gamma, the variable gamma, does vary very little. From 655 for 0 degrees Celsius to 681 for 40 degrees Celsius. At 20, which is a normal average temperature, is 0.668. And that is the reason why a lot of people consider that this number, if you don't know anything and you don't want to mess with it for a while, you can put 6.7 or 6.68, and that will do. And this is the chart in here, and the summary. And who do we have in here? Ira Sprague Bowen. He is the person that did so much work in this field of climatology and meteorology that somebody else afterwards ascribed this concept of this ratio the name of Bowen. Okay, to do that, I am also going to show the latter part of the video because it's interesting from a historical standpoint. Ira Sprague Bowen, 1898-1973, was an American physicist and astronomer. Bowen was the first director of the Palomar Observatory, which is here in San Diego County, serving from 1948 to 1964. In the field of meteorology, he's known for the introduction of the Bowen Ratio, which quantifies the ratio of sensible heat to latent heat over an evaporating surface. The ratio was named by the Norwegian oceanographer and meteorologist Harald Ulrich Sverdrup, who was the director of California's Scripps Institution of Oceanography here in San Diego from 1936 to 1948. So I'm given to understand that the Norwegian gentleman or scientist was already here, working in San Diego for Scripps, and he was either a good friend, a good professional acquaintance with Bowen. Bowen, at the time, a little later, as a matter of fact, from 48 to 1964, was the director of the Palomar Observatory. And like I said, Sverdrup decided to give this concept, ascribe the name of the concept, or give the name of the concept to Mr. Bowen. And I guess that's the way it was. And now we call it the Bowen Ratio. Very familiar topic for meteorologists and climatologists. Okay, so we already did the Penman-Monteith calculator, and interestingly, several years ago, I had a lady, a scientist, I think she was a biologist, I'm not quite sure, but I think she was. For the reason that I'm saying this is because she wanted me to do a Penman-Monteith, but for ecosystems, not for reference crop, because I was doing the reference crop because FAO wanted to do that for the reference crop to feed people around the world. But this lady, this scientist from Brazil, wanted it for ecosystems. So I did this calculator, which is the Penman-Monteith for ecosystems. And in here, we can do a calculation. We're given the air temperature, the net radiation, the relative humidity, the atmospheric pressure. Those are standard. And in here, we are going to define or tell the calculator what we're going to do for the resistances, for the stomatal resistance and the aerodynamic resistance. And what do? Well, I had to get a little creative in here in doing the calculator. So we say in here, choose 6A and 7B, or 6B and 7A, or 6B and 7B. So either three possibilities. Here we're going to choose, let's just choose tropical rainforest, 6A, and then 7B. No. I'm actually not going to run this model. I'm just going to show it to you. And 7B is aerodynamic resistance. Leave blank is choosing 7A. So we can leave blank in here and it'll run. This is an accommodation that I did for this lady to help her out, because obviously, as you realize very well by now, if this is such a complex calculation, that if you don't use a calculator that has already been built, you're going to spend your time doing this a long time, a lot of time. So I was able to help her out with her research, as I have, by the way, done for a lot of people. They asked me to do their calculators or to change their calculators so that they accommodate that to their research. So that is the Penman-Monteith calculator for ecosystems. And finally, we get to the extra meat of this class, which is the Shuttleworth-Wallace. Now, don't blame me if you think that this method is ridiculously complex. I agree with you, but I have nothing to do with it. I cannot change it. This is the Shuttleworth-Wallace method. However, I should say that the KISS principle has always been prevalent, and you guys know what that means. KISS means keep it simple, stupid, which means that the simple things are going to have more usage because there's a lot more that kind of people out there that they're very complex. So I do believe that at this point, the Penman-Monteith method is used quite a bit because it was ordered to be used by FAO, the United Nations. But I have yet to learn that the Shuttleworth-Wallace calculator, or rather that the Shuttleworth-Wallace method is widely used around the world. Nevertheless, this is a graduate class, so we got to present to you the new ideas. And this is a relatively new idea. Actually, not so new. The Penman method is dated 1948. The Penman-Monteith method, 1966. And the Shuttleworth-Wallace, 1986. What's the difference? Well, the Penman-Monteith method has two resistances, and they're difficult to get. We do get them, and there's some tradition and also experience with determining correct values, or more or less correct values, for these two resistances. Well, in the Shuttleworth-Wallace calculator, there's 5 resistances, because purportedly the Shuttleworth-Wallace calculator will do a complete calculation across the board of evapotranspiration types or evaporation types, because we know for a fact that there's 3 types of evaporation, and they're different, physically and chemically different. There's from surfaces, from water bodies, and from vegetation. And Shuttleworth-Wallace, they make the best effort to account for all 3. So with any further ado, let me just get in there. I was looking at it this morning. I always look to class in the morning just to make sure that I bring all things into the forefront of my mind, because sometimes, a year passes before I take a look at this. And I should say at this point that in this document there was a bug. There was a bug. And how did I find the bug? It was not a bug that had anything to do with the correctness of the method, but rather the show how it's visualized on the web. And it turns out that I was using the Chrome the Chrome browser, which I know many of you use, and there was a bug. I was really surprised. So then I said, oh boy, what is this? So I had to figure out where the bug originated. And it turned out that the bug originated with Chrome. So I switched back to Firefox, which is the browser that I normally use, and it was okay in Firefox. What had happened was that our student, graduate student, Rosa Aguilar, who helped me put this together, had worked with Chrome. Some people are more adept with Chrome and prefer Chrome. And she had decided to write some of the equations in Microsoft Math, or the math code. And I don't use that because it's kind of very cumbersome. And I don't like cumbersome things. But however, she's much younger. Maybe she was more adept at doing that. So she programmed it in math. And I believe that is, I'm not quite sure of this, but I think it's a Microsoft product. But the point is that she did it. And of course, it was not showing properly. So I had to come in here and fix it. And I fixed it for the Chrome visualization. Because as far as the Firefox, which is what I'm looking right now, there was absolutely no problem. Okay, so if you look at Chrome, there's going to be a few bugs in there in the display of the equations, which I hope to fix in the next couple of days. I don't like that. I don't like the fact that we have errors in visualization. So in here the evaporation using the Shuttleworth-Wallace method. I am not going to give a whole lot of time to this because I don't believe you are going to get involved in it heavily. I wouldn't ask you questions about it. The source of this is a paper. This is the source, I believe. No, she didn't put it in the source. Well, we can go back to the source. Shuttleworth and Wallace, 1985. I'm sorry, I did say 1986. No, it's 85. I believe I have the Shuttleworth-Wallace paper. I should put it in there. Clickable, so that people can see where the origin of this whole thing started. Okay, so we have first an introduction. We are doing this because we want to do the calculator. So we want to put all the equations in one place so that we can proceed to program that. We, by the way, I have told you this, but it bears repeating, we use PHP, which is a programming language, very good programming language that developed around the year 2000, 1999, 2000. It was such a great program that it allowed a lot of people, like the developer of Facebook, to get rich and famous. Zuckerberg, I guess his name is Zuckerberg. Zuckerberg got rich with PHP, as a matter of fact, and many others, by the way, that computer programmers that at the time they were learning this. I believe Zuckerberg was 19 or 20 years old when he did this in the year 2003, 2004. Can you believe that? Right now he's probably 40, bordering 40. But that's not the point. The point is that we wanted to do this here in writing, as I'll show you today, so that we can get it into the calculator. I'm not sure I'll have time to do the calculator, but it's easy. You can run the calculator. As a matter of fact, our calculators always have an example built into the calculator. So you can run, the example already tells you what the answer is going to be. So if you run the example, you're going to get the answer, and it will have to be the right answer. Otherwise, you made a mistake. You made a mistake in the input. So we have in here the Dalton formula, which we all recognize, 1803. Then we have the Penman formula, the combination method, which we all recognize, 1948. And the delta, we already recognize too. The Penman-Monteith formula, which I have already talked about this formula, both vector as well as raster today. And what Penman-Monteith or Monteith did is he added all these terms in here. Okay, and they're all defined in here, and all these numbers that you see in here, I have already talked about. Then the Shuttleworth-Wallace. What did Shuttleworth-Wallace do? It's a combination equation based on the Penman-Monteith method. The calculation is based on physical properties of the resistances from the plants in the soil or water which they're growing. So in here we have 5 resistances. Can you believe that? If 2 resistances were already hard, you can imagine. So these are the equations as shown and written by Shuttleworth-Wallace. Some of them are theoretical, some of them are empirical, some of them are conceptual. It is a hodgepodge of methods and stuff in here. Then they calculate that PMC, the Penman-Monteith C, and the Penman-Monteith S, and all these numbers that you see in here. Don't expect to understand the meteorology or the physics of this. I don't even understand it, okay? But it is correct in terms of what they said in their paper. And we actually did calculate the example that Shuttleworth and Wallace had put into their paper, so we believe we are fine. Isn't that ridiculous? Now we have an air sub A, air sub AA, air sub AC, R sub AA, aerodynamic resistance between canopy source height and reference level. R sub AC, bulk boundary layer resistance with the vegetative elements in the canopy. R sub AS, so when we talk canopy is vegetation, but then we're going to have the substrate, that's the soil. R sub AS, aerodynamic resistance between the substrate and the canopy. R sub SC, bulk stomatal resistance of the canopy. R sub SS, surface resistance of the substrate. So 1, 2, 3, 4, 5 resistances that need to be either calculated, estimated, or whatever way before you can run the model. Everything else is known. We have the online calculator, can be accessed by clicking on this link. Okay, and there's a calculator over there. And we have an example. Let me see if we put the sample input. Yeah, we do have the sample input in there. So in here, we can go to the sample input. And the sample input is going to be air temperature 25, mean boundary layer 25. So we go back in here, air temperature 25, mean boundary layer 25, mean stomatal resistance 400, and projected area 4 and 42. So 400, projected area 4, and aerodynamic resistance 42. I'm hoping I'm doing this right in here. Then aerodynamic resistance 128 and 0 and 400. So aerodynamic resistance 128 and 0 at 400. Then vapor pressure 1,000.7 and 101,325. Vapor pressure 1,000. Extinction coefficient, and to be honest with you, I don't know exactly what that means. And this one is, I forgot. It's 101,325. That's the atmospheric pressure. 101,325. In pascals, not in millibars, but in pascals. Okay, so we're ready to go. So the evaporation from the complete crop is 1.112. 1.112. And in the sample input, 1.112. So I correctly inputted all the data in the example of the Shuttleworth-Wallace paper. So with this then, I have shown to you that there's these 4 methods, namely the Blaney-Criddle, 60 years old, the Thornthwaite, also 60 years old, then the Penman-Monteith method, which again about 60 years old too, but a good method because it's conceptual, it's not empirical. Remember, I did mention to you in the past, several times I believe, that there's a hierarchy of models in hydrology. The top models are deterministic. The second level or second tier are the stochastic. So when you give up on the physics, that you can always resort to the games of chance, stochastic. The third level is the conceptual, and the fourth level is empirical. So when you give up totally on deterministic, stochastic, and conceptual, then you can always go back to empirical. The problem is that the empirical is the lowest tier because it does not apply globally. Well, the conceptual methods have a tendency to apply globally. Even though they are not as good as the deterministic methods, we're giving up because nature is very complex, both space and time, and when we cannot do it all, we have to give up. Example. Next week, we're going to talk about infiltration. I'm going to begin the subject of infiltration, and I'm going to spend a week talking about infiltration. And the first method that we're going to talk about is the run-up curve number, which is a conceptual method. So the case is made for conceptual methods. And the Penman-Monteith is a conceptual method. Okay, we'll see you then next, today is Wednesday, we'll see you next Monday. The subject is going to be infiltration, both Monday and Wednesday. Good night.